So we already know how to use Taylor series analysis to analyze accuracy. This lecture is about how to use eigenvalue analysis to analyze stability. Okay? So first of all, let's analyze the most acute question we have is why does the red scheme blow up? It's actually pretty easy to analyze why the red scheme blow up by doing this. Okay, so let's actually close this picture and solve a different ODE. Solve an ODE that is actually a lot more simple. Let's solve du dt equal to 0. The basic criterion for a scheme to be stable is that it should be able to solve this equation in a stable way. Okay, and let's look at the fourth order scheme we have. Okay, so it is u at the next time step is equal to, this is the scheme we derived, 8 times u at the previous time step minus 12 times dt times du dt, right? So here is the du dt that we replaced as minus of u in the last lecture, right? So let's actually, so for those who actually may not remember, the scheme we used is du dt is going to be approximately equal to minus u, so this is at a particular t, minus u at t plus 2 delta t, okay, plus 8 times u of t plus delta t, minus 8 times u at t minus delta t, plus u t minus 2 delta t, divided by, I think, 12 delta t, right? Let me see. Yeah, 12 delta t. Okay, so this makes our ODE solver to be the following. The only term that should be moved to the right hand side is this, to the left hand side, right? Because this is the most recent time step. And then what we derive is u at time step. For example, let's say step n is at t plus delta t, then u at step n plus 1, which is this term, needs to be equal to, moving to the left hand side, 8 times un, so that's this term, right? Plus, sorry, actually minus 8 times un minus 2, which is this term, right? So this is n plus 1, this is n minus 2, this is n minus 3. And this du dt is actually n minus 1. This is when I'm saying this is, I'm integrating time, right? This is at my step n is at time t plus delta t. Here, I'm trying to predict what is the solution at t plus 2 delta t. My n minus 1 is then t, my n minus 2 is then t minus delta t, and my n minus 3, the last one I need to use, is at t minus 2 delta t. Right, so by following this, I get minus 8 this term, and I have plus u n minus 3. Okay, so these are these three terms taken care of, and the last term I have is I need to also multiply the 12 delta t onto the left hand side, so I have minus 12 delta t times du dt at the nth step. Oh, sorry, actually n minus 1 step. So if I know my du dt is always equal to 0, this term is actually gone, right? So I'll just get rid of this term. So for example, here I'll say ... and comment out the later, right? So then I'll basically be solving du dt equal to 0. And let's see, if I run the section, I get the same thing. I get 10 to the 85. So I'm not even able to solve du dt equal to 0. While for this one, I wouldn't have this problem. So let's for example, I'm going to comment out the dt term. I should be able to solve du dt equal to 0 with no problem, right? So here I'm well, oh, okay, so I still have a problem, right? So I basically I still have oscillations, but the oscillation isn't growing. So remember, this is 0.95, this is 1, right? So I'm basically constantly oscillating between 0.95 and 1 for the second order scheme. But at least the oscillation is not growing, it's keeping constant. So I'm still approximately solving the du dt equal to 1 problem, all right? While for the fourth order scheme, I'm completely blowing up. So how do you know in advance if the scheme is going to work? All right.
Check stability.
Check the stability. Well, one thing is that if you think of this, what we just saw, why is the scheme oscillating between 1 and 0.95? It's because I actually started with the forward Euler scheme. All right. And the forward Euler scheme actually is not going to be a solution of the exact problem. The forward Euler scheme is actually solving still the ODE equation. What if I actually change the forward Euler scheme to be actually still solving the same problem? So let's see actually what happens. I was actually having a slight inconsistency, right? I'm using forward Euler for one time step, but solving the wrong problem. So this time, let's actually run the right. Okay, so I'm still plotting the analytical solution here, which let's ignore that for now. So now forward Euler is actually solving the du dt equal to 0. Okay, my second order, let's run. Okay, then the second order black line, I'm getting a good solution here. Fourth order, let's see. Okay, red, I'm getting a good solution here. What's the difference? So why in the previous case I'm getting 10 to the 85, while in this case seems to be solving the equation du dt equal to 0 with no problem? What did I change? The first few steps, right? I just changed the first few steps. In the current case, my first few steps are actually solution to the correct equation. While in the previous case, my first few steps are just a little bit off, not much. And that small error in the first few steps turns out to be an error that is as large as 10 to the 85 in later stages. That's actually an example of what instability is about. Instability is about magnifying an error from a very small one to a very large one. Instability is actually not guaranteed to be something that blows up. Instability will not cause your solver to blow up if you make 0 error everywhere. It's actually about if you make small error, instability is going to magnify the error, sometimes to very dramatic results.